Welcome to The Explainer. Today, we're looking at an absolute unsung hero of safety-critical hardware. I'm talking about the Texas Instruments Hercules TMS570 LC4357 microcontroller. We're going to explore the incredibly complex, completely invisible world of embedded hardware that operates all around us. Specifically, we're focusing on a piece of silicon engineered for environments where failure simply isn't an option. Okay, let's dive into this. Picture this. You're cruising down the highway, and suddenly, you have to slam on your anti-lock brakes. Or think about an aircraft adjusting its avionics mid-flight. In those moments, you aren't relying on standard, run-of-the-mill computer chips. No way. You're relying on automotive and aerospace-grade microcontrollers where the stakes are, quite literally, life or death. The device we're examining today is built from the ground up to shoulder that immense responsibility. Here's a quick look at our agenda for today. We'll explore the Hercules microcontroller itself, how it wakes up through its power sequences, pin characteristics, clocks and internal registers, and finally, its built-in safety features. Think of it kind of like a pilot's pre-flight checklist. Let's start with Section 1, the Hercules microcontroller. This little piece of silicon packs a serious punch. It runs on dual-ARM Cortex-R5F CPUs that can clock up to 300 megahertz, and it delivers a super-efficient 1.66 DMIPS per megahertz. Physically, all of that processing power is housed in a dense 337 ball grid array, also known as a ZWT package. And out of those connections, up to 145 pins are available purely for general-purpose I/O. That gives system designers a massive amount of flexibility to connect up sensors, actuators, and communication buses. So, why does all of this matter? Well, the real-world applications for this hardware require absolute, unquestionable reliability. We're talking about things like anti-lock braking systems, active driver assistance tech, electric power steering, railway communications, and highly complex aerospace and avionics arrays. Look, if the microcontroller in your smart TV crashes, it's annoying. But if a chip fails in one of these systems, it's a disaster. Moving on to Section 2, waking up power sequences. This device is actually divided into 6 distinct logic power domains, labeled PD1 through PD6. PD1 is unique because you literally cannot turn off all of its clocks at the same time. The other domains, PD2 through 6, are managed by a power management module, which can seamlessly transition them between on, idle, or off states. When a domain is pushed into that idle or off state, its internal clocks are completely stopped. This off state acts as a controlled shutdown sequence, which successfully removes the dynamic current, though it is important to note that a tiny bit of leakage current will still stick around. Now, once power is actually applied, the chip doesn't just instantly blink on. It goes through a highly choreographed startup sequence that honestly feels a lot like starting up a jet engine. First up, the high-frequency oscillator has to start and be validated, which takes exactly 1,024 oscillator cycles. Next is the eFuse auto load, which is essentially loading up the permanent hardware configurations, and that demands another 3,650 cycles. Then, the internal flash pump powers up over 250 cycles to provide the necessary voltage for memory. And finally, the main flash bank powers up, requiring an additional 1,460 cycles. If you tally all of those phases together, you get this number, 6,384. It takes exactly 6,384 oscillator cycles for the system to complete its internal startup checks. It's only after this exact sequence is successfully completed that the CPU reset is finally released, allowing the processor to fetch its very first instruction from address 0.
All right, Section 3, pin characteristics and configurations.
Now, what's really interesting here is the sheer level of control engineers have. Whether they're configuring a digital in, a DI, or a digital out, a DO, designers have to carefully consider and set the default pull state. This is absolutely crucial because it ensures that even before the software fully takes over, the hardware lines default to a known, stable electrical state. This prevents any erratic, unpredictable behavior in the connected external devices. And it goes even deeper. Configuring the output buffer drive strength is absolutely crucial. This setting literally determines the physical electrical force the microcontroller uses to push a signal down a wire. You have to ensure the MCU can physically drive external components safely without overwhelming them with too much power or falling short and losing the signal. It's all about preserving the integrity of the data being transmitted. A perfect example of this highly specialized pin configuration is the VCC PLL. This is a dedicated 1.2-volt nominal core supply pin built specifically for the phase-locked loops. You see, critical internal timing mechanisms require their own dedicated, exceptionally clean power sources. They have to be completely isolated from the noisy power lines that are feeding the rest of the chip's general functions. Another critical set of pins are the analog inputs. This chip features an array of input pins feeding two entirely separate 12-bit multi-buffered analog-to-digital converters, or MIB-ADCs for short. There are dedicated channels, plus 16 shared channels between MIB-ADC1 and MIB-ADC2. Think of this as the sensory nervous system of the microcontroller. It's how messy, real-world analog data, like the exact pressure you're applying to a brake pedal or the temperature of an engine block, is captured and instantly translated into perfect digital information that the CPUs can act on. Section 4. Clocks and internal registers. In a safety-critical system, you can never, ever assume your memory is clean on startup. Instead, you use specific software keys like the Mini TGCR and MS-INANA registers. These dense-sounding register names actually command the hardware to physically scrub the on-chip SRAM to a known, safe state. This process automatically generates the necessary parity or error-correcting code data. It guarantees that by the time the CPU starts reading and writing data, the safety nets are already in place and active. To keep all of this perfectly coordinated, the chip relies on its clocks. But it doesn't just have one heartbeat. It features multiple redundant clock sources. There's a main oscillator, low and high-frequency internal reference oscillators at 10 MHz and 80 kHz, multiple phase-locked loops, and external clock inputs. A dedicated global clock module maps all these sources out. This ensures that if one clock suddenly fails, the chip can instantly fall back on another, never losing its critical timing when it matters most. Finally, Section 5, built-in safety and self-test. So, the crucial point here, and this is where it gets truly amazing, is the BIST, or built-in self-test logic. The CPU self-test controller effectively interrogates its own processing cores. By using a deterministic logic BIST controller as a dedicated test engine, the chip rigorously tests its internal logic gates right at startup or even actively during operation. It's constantly guaranteeing that the actual physical hardware of its brain hasn't degraded. But wait, the safety measures go even further. Remember how we mentioned earlier that this chip has dual ARM Cortex-R5F CPUs? Well, they operate in perfect lockstep. That means two entirely separate physical processors are performing the exact same calculations, cycle by cycle, simultaneously. The chip constantly compares their outputs. If a spike of radiation, electrical noise, or a random hardware fault causes one CPU to flip a bit incorrectly, the outputs won't match. The chip instantly knows an error has occurred. Watching over all of this is the Error Signaling Module, or ESM. It's the ultimate overseer, continuously monitoring those lockstep CPUs, the memory ECC, the clocks, and all the self-tests. If the absolute worst happens and a critical, unrecoverable fault is detected anywhere, the ESM triggers the external N error pin. This acts like a massive red flare to the rest of the vehicle or aircraft, safely forcing the wider system into a fallback or failsafe mode before disaster strikes. It really is a masterclass in redundancy and failsafe engineering. So I'll leave you with this final thought. The next time you're driving your car, step on the brakes, or fly in a plane, ask yourself, how many millions of flawless cycles is a microcontroller like the Hercules executing right at that very second? Scrubbing its memory, checking its dual processors, and monitoring its heart rate, all just to keep you safe. Thank you so much for joining me for this explainer. I really hope you found this dive into the invisible world of embedded hardware as fascinating as I do.